so boundary conditions, right? This is super important. Applying the appropriate boundary condition. Yeah, I think this is one of the biggest errors I see in students doing this. The wrong boundary condition gives you the wrong result. It's that simple. Don't fix apart everything that it interfaces to, okay? You need to understand the actual degrees of freedom of that part. You want to make sure all degrees of freedom of a rigid body are constrained, like I just talked about, but not unnecessarily constrained. Do not over-constrain it, right? So the FEA will give you a warning if you under-constrain it, like I just mentioned. It's not going to tell you that it's over-constrained, because the blessing and curse of FEA is it can solve indeterminate problems, right? So it's going to give you the answer, even though the part's probably not constrained properly. Constraints are applied to nodes. So for solid mesh, this is another thing to remember. I don't know if I have this in here, but solid mesh. So for a solid mesh, the nodes translate. They can't rotate. They just translate. So they have 3 degrees of freedom. So solid mesh has 3 degrees of freedom. When you do beam, like solid elements, it has 6 degrees of freedom at the node. So you can constrain 6 degrees of freedom. But for a solid mesh, it just has 3 degrees of freedom. So if you do fix, you're fixing all just translations of nodes. So if you picked like the bottom edge of if you had a square beam that went into the page, right? And you're like, well, I want to fix this, but not the whole face. Maybe I'm worried about Poisson's ratio, so I'm going to fix this bottom edge right here. And you just fix that, right? Well, all that's doing is preventing those nodes from translating, but it can rotate, right? It's going to be under constraint. You're going to get an error because it's going to be able to spin about that line, right? Because the nodes can't rotate. You're not constraining rotations of nodes. So you'd have to also, the best thing would be to also fix this up here or something like that, right? If you fix something, the nodes right above it, then you're also going to get really high stresses here because it's a small area to react that around, right? So you're essentially not using this geometry anymore as your support. So just remember when you fix a solid mesh, you're fixing nodes, and for solid mesh, there's only 3 constraints, and they can still rotate. For plates and beams, it's 6 degrees of freedom, so you can fix. So if you did that plate again, really, if this was a 1D, you would have a node in the center, right? Because it just knows the geometry. So yeah, this you can control the 6 degrees of freedom. That's the other beauty of doing the 1D mesh, is that you can just give it exactly what degrees of freedom you want that end to be, and not have to worry about having a whole solid face and figuring out how to actually constrain that properly. And this might make sense on the next slide. Okay, so this is for if you have plates or beams where the nodes have 6 degrees of freedom. I thought I wrote this down. I'll try and edit this and make sure that's obvious. So it's obvious from this view. So this is SolidWorks. So here, when you go to a constraint, and I use this reference geometry, I like using that because you can just put your 6 degrees of freedom in and understand it, as opposed to saying, trying to figure out on a flat face how many degrees of freedom you want. I just pick the nodes that I want ahead of time, or I pick a face ahead of time, which would go in this box, and then you pick this direction. So if you pick like its vertical axis, that's what it's using as like vertical. And so if you're constraining something, you put a 0 here. You're saying it can't move. Like these are grayed out. This means it can move. You need to activate that cell, and you put a 0 in there, which means it can't move in that direction. You can remember that formula, right? Force equals KD. You can also put it, if you don't know the force is, let's say you had a beam and you had some weight on it and you had no idea how heavy that weight was, but you had a measurement of the deflection of that beam. You can put the deflection in instead and it'll give you the stress. So put a 0 anywhere you want to constrain it. Okay, so for plates and beams, you're going to see 6 of these because they have 6 degrees of freedom. Okay, so you have to do translations and rotations. So if you do fixed geometry, you're going to fix it. So these are, this is obvious. So this option is if you choose reference geometry. These are the standard ones you can just click and you won't see this window at all. So when you click this, it's automatically putting zeros in here for you everywhere. Okay, so this is like the shortcut to do that. I like to do it myself so I fully understand the constraint that I'm putting on it. But you can use these if you know what you're doing. So fixed geometry, it's gonna fix 6 degrees of freedom. It's gonna put zeros in all of these for you. Okay, that looks like basically like a cantilever beam, right? That's a fixed support on the end. If you pick immovable, no translation, it's gonna put a 0 in these translations, 0, 0, 0. Okay, that's like a pinned constraint. So it's gonna look like, a pinned beam. If you do a roller slider, that's obvious, it looks like a roller slider. It's 1 degree of freedom. It can only constrain up and down. So it's gonna put a 0 here. That's all it's gonna do. And then you have this fixed hinge, which constrains 5 degrees of freedom. Basically, it lets you rotate about one of these will not be, everything is going to say 0 except for like one of these, depending on what face you chose. And this is useful for Baja and Formula because this is like a clevis joint, right? This is like where your suspension goes into the frame, right? You can use a fixed hinge in that case. And that's what this looks like here. This is the highlighted fixed hinge. Any questions on that? Because boundary conditions are the bread and butter of running a proper analysis. Okay, so this is solid mesh. So it's the same thing, but if I do a solid mesh, you'll note that there's no rotations here, right? It just gives you translational options, okay? So if you do fixed geometry, what's it gonna do? It's gonna fix just the translations, okay? Now, if you do the whole face, it'll look like this. But I gave you a little bit of a warning. I think I might have said that here. That's what this note says, is what I just drew, that if you do this just to a line, it's not gonna look like a cantilevered beam like that, okay? Or just to a single node. You have to do it to a face to actually get it to be fixed, or multiple nodes. Immovable, these are exactly the same if you have a solid mesh. Because this is going to translate, this is going to do no translation, and guess that's the same thing as fixed. So actually, so it fully constrains. I should have changed. I meant to change this picture actually. It's the same thing. It fully constrains 3 degrees of freedom. So theme will determine if it's a pin or a beam. If you're selecting a face or you're selecting an edge or a single node, will change what this looks like. Toggling this won't change anything in solid mesh. You'll get the same results between these two. Roller slider is the same thing though. It's 1 degree of freedom. And then fixed hinge. And again, you need to make sure this is applied to a cylindrical face to make sure it's a hinge. My other warning here says, yeah, that's right. If you were trying to pin something, so you can get a lot of, again, you can see why solid meshes can be a problem. If you were trying to create this and you pinned an entire face, you select the entire face and you hit pin, you actually created this constraint. Because you're pinning multiple nodes on a face, and now it can't rotate because in order to rotate, the upper nodes have to move relative to the bottom nodes, and you're fixing all of them. And so, again, this depends on what geometry you choose in solid meshing.